All right, I want you to think about the last video game that just made you stop and stare. You know? Maybe it was the way the sunlight cut through the trees in a game like Red Dead Redemption 2, or, oh, how the neon signs just bled into the rainy streets of Cyberpunk 2077. That incredible, breathtaking realism? It's not magic, it's code. And today, we're going to pull back the curtain and unlock the secrets behind all of it.
It's a fantastic question, right? Is it just pure artistic talent? Or maybe just raw computing power being thrown at the screen? Well, the truth is, it's this powerful fusion of both. And they meet in a really fascinating piece of tech that's sitting inside your computer or your game console right now.
So let's start with what's actually going on. How is this magic happening on your screen? The answer begins not with software, but with a very, very special piece of hardware. It's designed to do one job, and one job only: create images. At the very heart of all this is the GPU, the graphics processing unit. Just think of it as a dedicated visual powerhouse. Your main processor, the CPU, that's kind of like the general manager of your whole computer. But the GPU, it's a specialist. It was built from the ground up to perform the millions and millions of tiny calculations needed to draw, or as we say, render, that final image you see.
But a powerhouse like that can't just guess what it's supposed to do. Nope. It needs incredibly precise, lightning-fast instructions. It needs to be spoken to in its own native tongue.
To really get this, let's use an analogy. It's a great one. Think of your CPU, that's like a master chef. A genius, right? It can handle these really complex step-by-step recipes with incredible precision. The GPU, on the other hand, is like a massive army of line cooks. Now, you're not going to ask that army to whip up a 5-star gourmet meal, but you can ask every single one of them to chop an onion at the exact same time. And that's the whole idea behind what we call parallel processing. It's all about doing thousands, even millions of simple, identical tasks all at once. And for graphics, which involves coloring millions of pixels, that is a genuine superpower.
So you've got this army of cooks, right? Well, they need a recipe book. It doesn't have to be complicated, but it has to be perfectly clear, super concise, and written in a language they all understand instantly. No room for error.
And that recipe book, that is a shader language. And it's way more than just another programming language. It's basically the instruction set for creating virtual reality on a screen. This is the language that tells the GPU exactly how light should bounce off a car, or how a shadow should fall across someone's face, or even just what specific shade of red a single pixel needs to be in a tiny fraction of a second.
So what kind of recipes are we talking about here? Well, they're incredibly powerful. Shaders are what figure out the final color and brightness of every single pixel you see. They tell the points on 3D models how to move and stretch to create animation. And they are absolutely responsible for all those jaw-dropping visual effects. You know, the shimmer of water, the chaos of an explosion, all while making sure your game runs at a nice, smooth frame rate.
Okay, so we've got the hardware, that's the GPU, and we've got the recipe book, the shader language. But how does an idea in a developer's head, written as lines of code, actually become that glowing image on your monitor? Let's take a look at that journey.
This is a super fast 4-step process that happens, believe it or not, billions of times every second. First, a developer writes the source code, the actual instructions. Next, your computer's graphics driver acts like this universal translator, compiling that code into a format that the specific GPU in your machine can understand. Then, the GPU executes that tiny program running all the calculations for potentially millions of pixels at once. And finally, the output of all that hard work is the beautiful final image you see.
And this is where the whole system is just so brilliant. By handing off all this intense visual work to the specialized GPU, the main CPU is now free to focus on other big, complex jobs like the game's AI, its physics, or even just keeping track of what's in your inventory. It is a perfect division of labor.
So if you're a developer and you want to write these shaders, what language do you use? Well, just like with regular spoken languages, it often depends on where you're going, what platform you're targeting.
The whole landscape is pretty much dominated by two major players, HSL and GSL. And for developers, the choice is actually pretty simple. If you're building a game for a Microsoft platform, so a Windows PC or an Xbox, you're going to use HSL. It's part of their DirectX toolkit. For almost everything else, though, we're talking Linux, Android, PlayStation, Nintendo Switch, you'll be using GSL. That one works with the more open standards like OpenGL and Vulkan. So yeah, it really just comes down to where your game is going to be played.
Now, you might stumble across an older language called CG.
It literally stood for C for graphics. It was this really ambitious attempt by NVIDIA to create one single, universal shader language that would work everywhere. And while it was super influential back in the day, the industry eventually just settled on the two big ones we just talked about. So now, CG is pretty much just a cool piece of computing history.
All right, we've covered the tech, the languages, the whole process, but let's bring it all home. Why should you, as a gamer or just someone who loves movies, actually care about any of this? What's the real impact on your experience?
Oh, the impact is huge. And it's way more than just prettier games. I mean, yes, better shaders mean absolutely mind-blowing visuals, but they also lead to better performance and efficiency. For developers, modern languages mean they can build amazing stuff faster. And for you, especially if you're on a laptop or a phone, efficient shaders mean less power drain and longer battery life while you're gaming on the go. That's a huge win.
But, and this is a big but, creating these visual masterpieces is really, really hard. A shader that runs perfectly on one type of GPU might create bizarre visual bugs on another. And trying to find what went wrong, it's a nightmare. I mean, imagine looking for a single typo when thousands of little programs are all running at the same time. A tiny math error, like typing a 0.5 instead of a 0.51, could make a character's face suddenly stretch across the entire screen. It gets weird fast.
But even with all those challenges, the creative power that shaders give people is just undeniable. The source material we're looking at puts it perfectly, saying they allow you to define how pixels appear on a screen, how light reflects off a surface, and how 3D shapes move in space. So, in other words, they are the fundamental building blocks of any digital world. They're the paintbrush, the lighting rig, and the laws of physics, all rolled into one. And that brings us to a really fascinating place. As these tools get even more powerful and easier to use, the technical hurdles start to fade away. So the big question isn't just what's next for the technology, it's what happens when the only real limit is an artist's imagination. The future of all these digital worlds is being written right now, one shader at a time. Thanks for joining me on The Explainer.